Hey everyone, I want to do a little homework help video for homework number 5, which was never actually assigned. I messed up and didn't post it in the right module. So anyway, let's go look at it and get some work going, and I'll show you how it all works. So where is it? There we go. First assignment. So the problem is, or the first problem on the assignment is number 100. So we're going to start there. College finds 10% of students who've taken a distance learning class. 40% are part-time students. Of the part-time students, 20% have taken a distance learning class. So that's a conditional probability there, right? Of the part-time students means that within just the part-time students, so we're restricting our sample space to the part-time students. Within that, 20% have taken a distance learning class. So D is the event that a student takes a distance learning class, and E is the event that a student is a part-time student. All right, so the thing I really want to do more than anything else is draw a Venn diagram for this, but we're gonna have to do some calculating first. So they want probability of D and E. So we're gonna need to use the conditional probability formula. So let's get a whiteboard going here and write down everything. So we have probability of D equals probability of E equals, and I totally forgot what it's 10 and 40, but in some order, but I don't remember which one is which. So D is distance learning class, and that's 10%. E is part-time. Why didn't they call it P? I don't know. Anyway, E is part-time, and so that's 40%. So we got 10%, 40%. So let's go put those on there. Oh, and we know that, excuse me. Yeah, let's get those on there. So 10%. Whoops, where am I at here? 10% for distance learning class, 10%, 40%, it's part-time. Okay, and then they said within, so of the part-time students, so in other words, given E, the probability of D is 20%. So probability of the part-time students, that's E. Yeah, so probability of D given E is 20%. So let's write that down too. Probability of D given E is 20%. Now, I should make a point. I don't know if they ask about this later on the problem. I think it does, but I don't remember for sure. The probability of D and the probability of D given E are not the same. So these are not independent. These are dependent events, because probability of D changed depending on whether we're looking at E or not. Like just D in general is 10%. D, if we know that E has happened, is 20%. So those things are not, those things are dependent. So let's go see what the question's asked. So question A, probability of D and E. All right. So probability of D and E. So we're going to use the conditional probability formula that says the probability of D given E is probability of D and E divided by the probability of E. Remember that this one right here is always your denominator. And we have D given E and we have probability of E. So we're just going to multiply those together. So I'm going to rearrange this, right? If I multiply both sides of the equation by probability of E, I end up with probability of E times probability of D given E equals probability of D and E, right? And so this is what, 40% times 20%, 0.4 times 0.2 equals 0.08. So probability of D and E is 8%. Probability of D and E equals 8%. Okay, let's see what else we got. Probability of E given D. All right, so they told us D given E. Now we need to do E given D. So we're going to use the same idea. So probability of E given D, probability of E given D is probability of D and E over probability of D. So that is 8%, 0.08 divided by probability of D, which was 10%, 0.1. So this is 0.8. This is 80%, 0.8. So probability of E given D is 80%. Now, notice that that's quite large, right? So this says that of the distance learning students, 80% of them are part-time, right? So very high proportion. So at this point, I'm going to go ahead and look at what the question asks, D or E. Before I do anything else, I actually want to, well, I guess I'll do D or E and answer these questions, but I really want to draw a Venn diagram here, right? Just to reemphasize, if nothing else, how to draw a Venn diagram. Just because it's really helpful. So the things we need are probability of D, probability of E, and probability of D and E, because we need the middle for our Venn diagram. So here we've got this. So we're going to have whoop, D, whoop, E, and the universe of possibilities here. And so we want to start in the middle as always. So this is 8%. For the and the reason I want to do that is so now for D, I know that D has to total up 10%, and that includes the bit in the middle, right? So this is 8%. If the whole thing is 10, then there's only 2% remaining here. So this is 2%. And similarly for the other one, it was 40% for E. So this is 32% for E. And if we add this all up, we get 42%. That leaves 58% out here. That's 58% of students who have neither taken a distance learning class nor are part-time. So these are the full-time students who've only taken in-person classes is 58%. Right now, the visualization is really easy, and you can actually tell just by looking at it that within D, most of D overlaps with E, right? This picture's not to scale at all. If it were to scale, it would look something like this, right? Big E with like a little D over here. Or it looks something like that, right? Where this is D and that's E, right? Where this is 32%. This huge thing here is 32%, and this is 8%. I guess I still didn't draw it to scale, but you get the idea. And this is 2%, right? That's what it would look like if we were drawing it more to scale, a little bit closer. We don't usually worry about that, but if you want to draw your Venn diagrams to scale, it's not a terrible idea. Gives you a visual reference. A nice visual reference. So anyway, they didn't ask for this, but I think it's important to have a nice visualization whenever you can get one. So this is what your Venn diagram would look like. They asked for or probability of, I have it on select. Gosh darn it. They're making open and close the whiteboard panel. There we go. Okay, so probability of D or E. Well, we're going to use the OR formula. Now I'll go ahead and use the formula here, but I do want to emphasize that we actually can tell just by looking. D or E is just everything that's in the circles, right? One or the other or both. And if I add those up, it's 42%. There you go. Really helpful. Now that said, if you want to use the formula, probability of D, or that looks like a P, but it's actually a D. E is probability of D plus probability of E minus probability of both D and E, right? So D was 10%, E was 40%, and both was 8% plus minus, and then that equals 42%, which is exactly what we see here. And then they asked about independent and mutually exclusive, I believe, was the other bit. And so we can just handle it with those. Yeah, that one. So whether they are independent, as I mentioned earlier, they're not. They are dependent because the probability of D and the probability of D given E are not the same thing, right? So D changes probability depending on whether we know E is true. So D and E are not independent. They're dependent because doing one changes the probability of the other. Show whether D and E are mutually exclusive. This is really just a vocabulary question. D and E are not mutually exclusive because they overlap, right? They overlap 8%. In fact, 80% of D is in E. So they are very not mutually exclusive. It's actually quite likely that if one has happened, the other one has happened. All right, so 12 was the, 112. Oh my God, I scrolled way too fast. 112 was the next one. 112. 12. This guy right here. Okay, so complete this table. All right, this looks pretty straightforward. I don't think there'll be any trouble here. Yeah, we're just gonna fill that in. I'm gonna blow this up a little bit so that I can write on this part of the screen rather than having to make a whiteboard with a whole new table. All right, so we've got the totals, and we're just gonna like subtract basically. So let's annotate this. Red seems good. All right, so if the totals here are, so I suppose I should go ahead and read the question. Might as well, right? Something identifies a group of children by one of 4 hair colors and by type of hair. Wavy or straight? Where's the curly? Come on now. Some people have curly hair. We'll just lump them into wavy, I guess. So we got wavy or straight, and brown, blonde, black, red, and then the totals. So we're just going to go ahead and fill out the rest of the table and find some probabilities. I'll probably make a whiteboard for B through G. So yeah, let's blow this back up. And so for totals, we're going to subtract. It's going to be easy. Where's my, how do I annotate? Well, no, that's right. I have to reselect it, don't I? So 100. I hope it's clear that if the total here is 20 and there's 15 with straight hair, then there would be 5 people with wavy hair. I hope that's clear enough. Let's make sure that that works out here. 25, 43, total's 43. There we go. That's good. Our red total is 15. And then this total is 215. So I got 120, 135. So that means I need, I got 135 there. So I need 80 here. And so 15, and then straight black hair, I'm going to have 65. And then the total here, we could just subtract there, right? So that's going to be 172. 172. All right, there we go. We did it. We filled out the table. Not the greatest of challenges. Go ahead and erase all that. This back down to some readable size. Oh, I need to do this. Get that back down to some readable size here. Hello, computer. Well, let me scroll. There we go. Oh, okay. Yeah, what's the probability the randomly selected child will have wavy hair? I'm not even sure we need to bother doing this. So wavy hair total is 43 out of 215 people. So 43 out of 215 is the answer. What's the probability that a randomly selected child will have either brown or blonde hair? Well, the total here was 20, the total here was 100, so we got 120 out of 215. What's the probability that a randomly selected child will have wavy brown hair? So wavy brown is this box right here, so 20 out of the 215, so 20 out of 215. What's the probability that a randomly selected child will have red hair, given that he or she has straight hair? All right, so randomly selected child will have red hair given that he or she has straight hair. So we are restricting ourselves to just the straight hair people, which was 172. And what's the probability they'll have red hair given that they had straight hair would be 12 out of the 172. If B is the event of a child having brown hair, find the probability of the complement of B. So everything but brown. Well, there were 100 children who had brown hair. So the rest of the kids would be 115. So the complement would be 115 out of 215. What does the complement of B represent? Complement of B represents the event that a child does not have brown hair. That's it. All right, let's do the next one. What's the next problem? The next problem is 116. That is not the right thing here. I can just use page down. 116, is that the cookie one? That is the cookie one. All right, I like this cookie one. All right, box of cookies contains 3 chocolate and 7 butter cookies. Miguel randomly selects a cookie and eats it. Then he randomly selects another cookie and eats it. And if it was Jeff instead of Miguel, he would randomly select 8 more cookies and eat them too. All right, how many cookies did he take? How many? 2. 2, book. I can count to 2. Anyway, draw the tree that represents the possibilities for the cookie selections, right? The probabilities along each branch of the tree. All right, so we got 3 chocolate and 7 butter cookies. Who buys a box of cookies like that? That's not a real box of cookies. Come on. Anyway, let's go back to the whiteboard. So we got 3 chocolate, 7 butter, and he's selecting 2. Okay. So new question. So 3 chocolate, 7 butter. So I do love a good tree diagram, and this is one. So we got we're gonna go first cookie and second cookie. So we get second cookie here. All right, so we go. They said them chocolate butter. I'll do chocolate butter. It feels weird to do C then B, but that's what we're doing. CB, CB. And he had 3 chocolate and 7 butter cookies in a very disappointing box of cookies. All right, so 3 chocolate, 7 butter. So this was 3 out of 10. 7 out of 10. 10. And then if he's so down this branch, he's selected a chocolate cookie. So the probability of selecting a chocolate cookie goes down now. There's only 2 left out of the 9 remaining cookies. Right, so we got 2 out of 9 here, and this is 7 out of 9. There's 7 butter cookies left. If you select a butter cookie, then there's going to be a 3 out of the 9 cookies left are chocolate, and 6 out of the 9 left are butter. And now, certainly, we could reduce some of these, right? Like 3 out of 9 and 6 out of 9, but I'm not going to. I'm going to leave them the same. Leave them alone. And the reason that I'm going to do that is that it'll make the combining easier later. I don't actually know if we're going to need to, but probably. Right, so if I make this 1 out of 3, then I'll get 7 out of 10 times 1 out of 3 is 7 out of 30. But then if I need to like add that over here, I'm going to immediately have to turn the denominator back into 90. So I might as well just leave it. Yeah, so let's multiply out all these probabilities. I don't know if they ask us to. I'm sure they ask us to at some point. But let's see. So we're going to have 6 out of 90 here. 6 out of 90. For that branch, and then for this one we're going to have 21 out of 90 and 21 out of 90, and then this one is 42 out of 90. So notice that it makes them all nice and comparable, right? It's a little harder to tell what 7 out of 90 is when you compare it to like 42, or excuse me, what 7 out of 30 is if you compare it to 42 out of 90. It's way easier if the denominators are all the same, because then you can just tell, oh, 42 is bigger than 21. There we go. That one's bigger. Right, you could reduce them all, but there's just no good reason to. I forgot what they asked. Anyway, that's the tree diagram. Let's see what they actually ask us to do. Are the probabilities for the flavor of the second cookie that Miguel selects independent of his first selection? No, they're not. They change, right? You can see that from the tree diagram, or you can see it just by thinking about it. So the probability of selecting a butter cookie changes depending on whether you have selected a chocolate cookie or a butter cookie first, right? Butter cookies are 7 out of 9 if you select a chocolate one first, but 6 out of 9 if you select a butter cookie first. So they change depending on whether you've done C or B first, so they're dependent. Right, that's literally what dependent means, is if an event happens, does it affect the probability of the other event or of another event? And the answer here is clearly yes. For each complete path through the tree, write the event it represents and find the probabilities. All right, I guess I'll go write the events that happened there, and we already found the probabilities. Convenient. I kind of figured we were probably going to need to at some point. All right, so this is probability. I'm going to call it probability of CC. Sure, CC. Probability of CB. Probability of BC. And the probability of BB. Now, it's possible that what they wanted was something like C and C, C and B, B and C, B and B, and then these guys would be the same. But I actually don't know if later in the problem they're going to talk about the order mattering here. So I want to keep these guys distinct, even though in this case he's selected a butter and a chocolate in both cases. Just the order in which he selected them is different. Sometimes they ask a question in such a way that the order matters, and sometimes they don't. So for right now, I'm just going to assume the order is going to matter later, and I'll write them like this. What do we got? Let S be the event that both cookies selected were the same flavor. Okay, that's actually a perfectly reasonable letter for that. Find P of S. All right, so that's easy enough. So same flavor was this one and this one. So P of S, P of S is the sum of these two things, 6 out of 90 plus 42 out of 90, which is 48 out of 90. Now you could reduce that if you want to. I don't want to bother, so I'm not going to. Probability of, I saw the next one was a T, but I didn't. Probability of T, or T be the event the cookies selected were different flavors. You couldn't call that D? Anyway, find P of T by two different methods, by using the complement rule and by using the branches of the tree. Okay, so complement rule is to notice that T is the complement of S, right? Two cookies being the same flavor or two cookies being different flavors are clearly opposite events. And so we could say that this would be, we could add it up like this, 21 out of 90 plus 21 out of 90 is 42 out of 90, 42 out of 90, which is the same thing as 1 minus 48 out of 90. That's the complement rule, right? I would do 1 minus the other one, 2 out of 90. And you can see that they are in fact the same, which is good. It would definitely be bad if those came out different. Something would have gone wrong for sure. Let U be the event that the second cookie selected is a butter cookie. Find P of U. All right, second cookie selected is a butter cookie. So that means that the second cookie, the layer down here, is a butter cookie. So that means that we are looking at this event here and this event here, right? So this is a case why I didn't want to do something like this, where I didn't want to combine these because I wasn't sure they were exactly the same. Because now we're talking about specifically the second cookie, so the order matters. So that's 21 plus 42 is 63 out of 90. Great, that was easy enough. Let's do the next one. All right, let's see what the next problem was. I think it was 118. Is that right? I got my assignment over here. 119. Pardon me. So we're gonna flip over here to. Wait, what? The heck? This is the thing I set up. That's what I'm gonna post this later with my answers. 119. All right. So page down. All right. 119. Given the events G and H, P of G is 43%, P of H is 26%, P of H and G is 14%. Find the complement of that event and find the probability of the complement of the event H or G. So this is a really good problem. So it doesn't say it here, but you absolutely should draw a Venn diagram. That's going to make this so much easier. We're just going to be able to look at it so to answer the question. So G is 43, H 26, H and G is 14. All right, so I'll probably go back to this after I immediately forget these numbers. So probability of G, yeah, I think that was 43. And then H was 26, and in the middle was 14%, I believe. So 43 minus 14 is 29%, and 26 minus 14 is 12%. All right, so let's draw my little box, and then that leaves some other stuff out here. So this is 43 and 12 is 55%. So that leaves 45% out here, just languishing. That's not in either one. All right, and so from here, I bet we can probably do this really easily. So let me just, I guess we'll try this, right? G is 43%. Probability of H is 26%. Probability of G and H was 14%. All right. So let's go look at what the question asks for. Probability of H or G. All right. Probability of Horg, I guess. So probability of H or G. Now we could do what we did before in the previous problem asking about something like this, and use the formulas. And absolutely, if you're not comfortable with Venn diagrams, you should definitely do that. I'm feeling pretty good about Venn diagrams though, and I feel like I can just look at this and see. Right, 29 plus 14 is 43, plus 12 is 55. And so H or G is 55%. You could absolutely use the formula though, right? Probability of G plus probability of H minus probability of G or H. And it'll give you the same thing. Next question. Find the probability of the complement of, find the probability of the complement of event H and G. All right, well, that's actually pretty easy. H and G was, this middle bit here was 14%. So probability of the complement of H and G is 1 minus probability of H and G, which is the same thing as G and H. I don't know why they're doing H first when alphabetically G comes first, but so it's 1 minus 14%, which is 86%. 86%. And then I think that it was the complement of H or G. Complement of H or G. Yeah, so it's just 1 minus H or G, which is so H or G was 55, so it's 45%. So it's actually this guy right here, this complement of H or G. All right, that one was nice and easy. Let's do another one. All right, so next question is 123. Which one is this? Oh, the drivers. Yes, I love this question. So I love this question not because it's easy. In fact, it's quite a nuisance to do, given what they've well, the way they've presented the information here. This is why this problem. One of the reasons I signed this problem, by the way, was I want to convince you guys that tables are good. Tables contain a lot of information and it's very readable, as opposed to paragraphs, which can contain a lot of information and make it not very readable. So let's read. The percent of licensed U.S. drivers from a recent year, why don't you just say the year, that are female is 48.6%. Oh yeah, that seems crazy to me. Why is less than half of the less than half of drivers in the U.S. female? Because there are more women. I don't know if you know this, but there are more women in the U.S. than there are men, and it's primarily because women have a longer lifespan than men do. So I would expect that more of the drivers would be women. This is really weird. Anyway, of the women, females. Why didn't you just call them women? Weird. Of the females, 5.03% are age 19 and under, 81.36% are age 20 to 64, 13.61% are age 65 or over. Of the licensed U.S. male drivers, 5.04% are 19 or less, 81.43 are 20 to 64, and then 13.53% are age 65 or over. All right, so absolutely I want a table. Like 100% I want a table here. They say construct a table or tree diagram. Great. Oh, that's right. This is the one where I asked for both, right? We'll do the table first because it's a lot easier to manage. And you might notice that, so the thing I'm seeing here is that this adds up to 100% because we are looking at just the women. So this is a conditional probability, right? So of this 48.6%, 5.03% are age 19 and under. And of the 48.6%, 81.36% are 20 to 64. So I guess actually maybe I'm going to do the tree diagram first and then use that to do the table. Do that? Yeah, let's do the tree diagram first. All right, it's going to be a little bit messy. Let's go back to the whiteboard page. So we're going to get, so we're going to have men and then women. So let's do it this way. Let's go male, female. And within the men, we're going to have, I would call this 19. I guess less than 19. 20 to 64. We're just going to get 20 to 64. Oh, it's not picking up my finger very well, sorry. And then 65 greater than 65. And then the women I'm going to put in the same order. I'm not going to write it in just for neatness purposes. So we knew the women were, here, let's do these in blue like I did the other one. I like that. We knew the women were 48.6%. 6%. So that leaves 51.4 for the men. 51.4% for the men. Right, because it's got to add up to 100, of course. Yeah, and then for the men that were 19 and under, this was 5.04%. 5.04. not going to write the percent signs. It just starts getting a little bit messy. Just realize that this thing's a percentage, and so are these other ones. And then we had some other numbers of the men: 5.04, 81.43, and 13.53. Okay, 81.43, 81.43, and 13.53. 5.53, yeah. And then the women, same order: 19, 20 to 64, more than 65. Just not writing it for space purposes. We had 5.03, 81.36, and 13.61. Those are very, very similar. 5.03, 81.36, and 13.61. 5.03, 0.03, 81.36, and 13.61. All right, so first thing we got to do before we do anything else is figure out what the probabilities here are at the ends of the leaves. I'm going to need a calculator for that. Oh, I think I closed the calculator. I did. I'm going to go ahead and pause the video while I open up the calculator, because it takes seriously 3 minutes on my computer. So I'm gonna pause it here. Okay, calculator's finally open. We can share it up here. Fantastic. All right. So so what we can do is type everything in at once. And honestly, the thing you probably should do is do 51.4% times 5.04%, and 51.4% times 81.43%, and 51.4% times 13.53%. But I'm going to show you a trick. You don't have to do it this. You absolutely do not have to do it this way. I just want to show you some cool things your calculator can do. If you want to do a batch process. So what I'm going to do is I'm going to go to the calculator. I'm going to put the second of the what I'm trying to say here, the second of the variables into lists. I'm going to put them in list 1 and list 2. So yeah, so I'll do what is that? Oh my God, I've forgotten everything. I apologize. My brain has deserted me. I'm going to put 5.04, 81.43, and 13.53 into L1, 5.03, 81.36%, 13.61% into L2. And then I'm going to do, and I'll show you what we're going to do with that. So basically, I just want to show you a way to batch process a bunch of numbers to save you a very, very marginal amount of time, but really to kind of show you something cool that your calculator can do. All right, so let's go to here. Oh, it won't show I wish it would leave the whiteboard up while it showed me this, but it doesn't. It'll just close it. So I'm going to go sat at it, and I'll just get it off of the PDF that I've got open here. So we had 5 points. So for the men, I added men first, but they listed women. I should have done in the other order, but whatever. So I'm going to do 5.04, 81.43. I'll show you why I'm doing this in whole numbers instead of decimals in just a second. 13.53 here, L1, and then L2. We're going to do the women. We're going to do 5.03, 81.36, and 13.61. So I'm going to show you kind of a cool thing you can do. If I do, I guess I could just do it right here, right? So I could do in the header here, I'm going to do 48.6%. So 0.486 times L1, 0.486 times L1. So second function of 1, give me that. And then these are the percentages that go at the bottom of my tree. And then I'm going to go over here and do 0.514 times L2 times L2. And so I ended up typing a total of 4 fewer numbers than I would otherwise have. So this is very slightly quicker than typing them all at once. It also has the added advantage of not making you do one and then write it down, then do one, then write it down. But you can just do them all, and it just retains all the answers, which is really nice. Which is why that's probably the best reason to do it, to be honest. Right. So I'm just going to call this 2.45 and this one 39.58 and 6.56. We might have some rounding error. I think those all went up, so we might have a little bit of rounding error there, but not a big deal. Same thing for this. Right. And so I can just use all those numbers, which is convenient. Just have them all there to look at instead of having to write them all down and then go back and forth. So yeah, so this is, for the men, we get 2.45. So 2.45 here. And oh, by the way, I said I would tell you why I did whole numbers for these guys and then percentages for the other ones. It's because I wanted it to come out in percentage form. Like if I had done them both as percents, I would have to then turn this would come out to 0.02449, and I would have to mentally put them back. But by treating only one of them as percentages, it comes out in percentage form again, which is convenient. That's what I wanted. So that's why I did that. You certainly could put them all into percentages first, or you could leave them all as whole numbers as long as you move the decimal place two in the right direction. 39.58. And then the last one was 6.58. 6.58. And of course, these are all percentages. I just don't want to write all the percent signs on my screen. It's a little bit of a clutter problem. 2.59 here, 0.59, 41.82, and 6.99, so 7.00. So yeah, this doesn't, so you can see I came out to be 0.01% off here, and I think here as well, yeah, because everything just rounded up by coincidence. So we got a very, very tiny amount of rounding error. That's fine. It's not a big deal here. Okay, so then they said make a tree diagram or a table. I said make a tree diagram and a table on the homework. So I'm going to go ahead and do that. And the table is so much easier to read than this. Right, so we're going to have, which way do I want to do this? I want to do men and women across the top here. So MF less than 19, 20 to 64, greater than 65. I guess it's actually greater than or equal to 65 and less than or equal to 19. Yeah, sure. All right, so the men were 2.45, 5, and again, all percentages, of course. 39.58, 6.58, and then we got 2.59 here. 41.82. That's interesting. That's so different. Did I do that right? Let me. No. Something's wrong here. What happened? Why? 48.6 is smaller than 51.4, and 81.36 is smaller than 81.43. So when I multiply, this can't be 41.82. What the heck? What did I do wrong? Did I do the women first or the men first? Shoot, I've messed something up and I don't know what it is. Hang on. 5.04. And so that was the men. So this is 0.514 times. Oh, I did it backwards, didn't I? Dang. All right, so let me, so I see where I messed up. I switched them. Sorry about that. I don't know how to edit videos, so I'm just going to go ahead and leave these in. This first column, this was the men, not the women. And so I did 48.6 here. So I should do 0.514 times L1. I bet most of you probably caught that while I was messing it up. Yep, look at that. Then this one should be 0.486. And I didn't notice it until right now. But I hope the thing that you just saw me do, where I was kind of examining the numbers and comparing them as we're going along just to see if what I was doing was making sense. Like I do that all the time in my problems, and catches so many mistakes. Not all of them, but it does get most of them. So let's go fix all of this. So yeah, I messed all this up. So we're gonna get rid of that, all these guys, and we're gonna put in the correct numbers instead. Also, we're gonna get rid of all this because all these are wrong. Actually, the table was right. I could leave the table. So this was less than or equal to 19 M and F, right? That stuff was fine. It was the numbers that I needed to fix. So let's go fix them. So sorry about that if I messed you guys up here. So we got 2.59, 41.86, and 6.95. So we got 2.59 here, 2.59. Second one, 41.86, 41.86, and then the third one was a 6.95, 6.95. Hey, no rounding errors this time. That's nice. And then the other one, we've got 2.44, 2.44, 39.54. There we go. That's more what I was expecting to see. And then 6.61, 61. Oh, a little bit of rounding error there, but in the other direction, since everything got down. And that's fine. So, all right, so less than 19, men 2.59, women 2.44, 20 to 64, 41.86%, 39.54%, and then 6.95%, 9.5, and then 6.61, 61%. All right, we did it. I did part A. Let's go see what the other parts look like. Part B, find probability driver is female. All right, so that's, wait, they already told us that. Percent of licensed U.S. drivers that are female is 48.6%. It's 48.6%. If we didn't know that ahead of time, we could go add up the totals for, we go add up the totals that are on our whiteboard, right? We could add up all of these guys, but I don't need to because I know what it is. It's 48.6. So yeah, great. That's easy enough. Find the probability driver is age 65 or over, given that the driver is female. Oh, we know that already. They told us that in the problem too. Of the females, 13.61% are age 65 or over. So that's the answer, right? So we're restricting ourselves to just the women, and 13.61% of them are at least age 65. Find the probability the driver is age 65 or over and female. Aha, that one we need our table for. Age 65 or over and female, 6.61%. Great, that was easy enough. In words, explain the difference between the probabilities in C and D. In C, we are restricting ourselves to just the women and then figuring out if the driver is age 65 or over. In D, we are not restricting ourselves to in any way. So part D includes the men, right? The denominator includes the men here in D, and we're just looking at this one cell here out of everybody, not not conditional probability. So that's the difference there. So no restrictions in D. There's a restriction of our sample space to the women in C, but not in D. Find the probability that the driver is age 65 or over. All right, so here we're just gonna, so now we're looking at just this row here, 65 or over. So we want to add those up. What's that? 13.56%. So 13.56. That's what you get when you add those up. Like are being age 65 or over and being female mutually exclusive? Obviously not. There are women who are 65 or over, so clearly not mutually exclusive. How do we know? Because one does not preclude the other one. If you are a woman, it does not mean that you cannot be age 65 or over. And of the people who are age 65 or over, it is not true that none of them are women. That's how I know. Suppose that 10,000 US licensed drivers are randomly selected. How many would you expect to be male? 51.4% of them? Yeah, 51.4% of 10,000, which is 5,140. Using the table or tree diagram, construct a contingency table of gender versus age group. Didn't I do that? Gender versus age group, we did that. That's what they... Oh, for the 10,000 people. Okay. It's like, wait a minute, I'm sure I did that. So they want gender versus age group, and they want a contingency table, but they're saying, okay, if we had 10,000 drivers, do that. Okay, so all you want to do is move the decimal place 2 to the right in each of these cases, right? So 2.59% is 0.0259. So we move it 2 to the left to get the percentage, and then 4 to the right because we're multiplying by 10,000. So the net decimal movement there is just 2 to the right. So 259, 244, 4,186, 3,954, 695, 661. There you go. I was going to say, I'm almost positive we did that already. Okay, using the table, find the probability that of the age 20 to 64 group, a randomly selected driver is female. Okay, so we're actually going to have to do a calculation here. So in this group, in this middle group, find the probability that the driver is, that a randomly selected driver is female. So what we're going to do is we're going to say, well, the total of this group is 4186 plus 3954. What's the probability that we picked a woman at random? So it'll be 3954 out of the total. So let's go to the calculator. 4186, 3954. Okay. So 4186 and 3954. So that's the total that we've got there. Sorry, it's off my screen. 8,140. So it's going to be 3954 out of 8140. So there's your probability, 48.57%, which is unsurprisingly very close to 48.6%, right? It's not exactly 48.6% because the 48.6, 51.4% doesn't hold for every age group, only all the age groups in aggregate, but it is unsurprisingly quite close to 48.6% because that holds mostly. So 48.57% would be your answer for 124C. And that is the end of the homework, I believe. Let me go have a quick look at my assignment. Where are we at here? Yeah, 124 is the last required problem. So there you go. So that is the end of the homework problems. So I'm going to go ahead and stop the video here, and I'll see you in the next one.